All right, so let's start. Before we go further with our discussion related to RTL, uh, there's one clarification that I want to go through before we proceed further. If you recall, we had seen this very simple example of design at the RTL level, and we had obtained this particular ASM chart, and we had obtained this particular corresponding data path and a controller. Now, a question that arises when I write something like, let's say, R5, when I write a statement like this, R1 plus R2 are added together, and the result is put in register number R5. Now, when does this occur? When does the register transfer actually occur? So, for example, let's look at, so state S0 is in first clock cycle, state S1 is in second clock cycle, and so on and so forth, right? So let's look at this particular one. When does the transfer actually occur? So if we take the view that state S1 starts here, right? Once I have this clock edge comes in, my system goes to state S1. So if I take the view that the contents of R, after adding R1 plus R2, whatever is the sum here, is transferred to R5 at this particular point here, when you enter state S1 at this particular clock edge. Then, as we were discussing, if you take that particular view, then all the addition and all that should have taken place in the previous state. Right? It should have taken place, addition and all that should have taken place in the previous state. And in order to do that, all the select signals that are required, for example, this may be an adder subtractor block, so I have to select addition here. Plus, in order to load into R5, I'll have to enable LD5 and all that. So all those signals should have been enabled in this clock cycle. Because you have to take all the actions in this S0 state so that the result can be latched on this particular one. If you say that the actual transfer occurs at this particular clock edge, then everything should have taken place in the previous clock cycle. On the other hand, if we take the view that R1 plus R2 that transfer to R5, that what really happens is addition occurs in S1 state itself. Addition occurs here. So I enable all the signals, all the control signals that are required to carry out this operation. Everything takes place in this state S1. But then, if it takes place in S1, where will it be latched into the flip-flop? At this clock edge. It will be latched at this clock edge. Right? So, one view, one can take is that, well, the actual transfer occurs at this clock edge when you enter state S1. But then, there's a little bit of a problem here. All the control signals and all that you should have enabled here in the previous state. That's confusing because I'm writing in state S1 that this operation is taking place, but all the control signals have to be generated in the previous state. So that's a little bit confusing there. On the other hand, if I say, well, this entire operation, addition and everything is taking place here, all the control signals to carry this out is also generated here. The only thing is the actual result becomes available in R5 at the end of this clock period when the next edge comes. Okay? So let's take, this is a better view, less confusing view, and this is a more common view. That when I write something like this, R5, R1 plus R2, the operation is taking place here, but the result will become available in R5 only at this particular point, as you enter into the next particular state here. So, okay, at this particular clock edge. All right, so the point was, when does the register transfer actually take place? So let's keep that in mind. It will actually take place at the end of this particular state here, when the next clock edge comes. Okay? All right. And so then the control signals and all that, remember, so if I have to do R5, R1 plus R2, then the control signals, when I'm in this particular state, the control signals will have to be generated, all in this particular state itself, corresponding to this particular operation. So that's easier rather than saying for this operation generated here. Okay? All right. So here things were a little simpler in the sense that we were simply going from one state to the next state and so on and so forth, and looping at the end of it. A more realistic case is where, for example, there are conditional statements. For example, again, a simple example. Let's say what we do is we read all this data here, A, B, C, D, and X here. There's an operation that I do. Z1 is A plus B plus C plus D. Fine. If X is 0, X is a 1-bit number. If X is equal to 0, then I do, there's a second output Z2, which is A plus B multiplied by C. Else Z2 is A plus B into C plus D. And while, and then you continuously loop here. So you continuously do that in a loop. So we have to produce two outputs, Z1 and Z2. And there are 4 inputs, A, B, C, D. And these are all, let's say, 4-bit numbers, and X is a 1-bit number. So we have to do that. We have to write an ASM, obtain an ASM view of this particular one. So let's see whether this makes sense. So I read R1, A, R2, B, R3. We read all these things here in these registers, R1, R2, R3, R4. This is a 1-bit register. We're calling it a flag. So flag is high or flag is low, so it's a 1-bit, so flag. So you're reading this X into the flag here. Then you're doing R1 plus R2. So you're doing A plus B is available here. Then you're doing R3 plus R4. So C plus D is available here. So these are all straightforward statements, S0, S1, S2. These are just like before. Now, this state is interesting. This particular state here. Note this particular state here. It's interesting because several things are happening in this state. One is S3. So this box is known as the state box. So in this S3, I'm doing R7 is R5 plus R6. Okay? It doesn't depend on any condition. So because the first result A plus B plus C plus D is independent of any condition here. So I'm adding R5 and R6 and writing it in R7. So that produces A plus B plus C plus D. So result is available in R7. Then in the same state, this is one single state. In the same state, I'm testing F5. I'm testing F5. If F5 is, let's say, 0, then I'm doing this. Say if F5 is 0, I'm doing one kind of operation. If F5 is 1, I'm doing another kind of operation. So basically doing A plus B into C. So this is A plus B. R6 had what? So I should have done here R5 into R3, right? R5 into R3 would have done this operation, A plus B into C. And R6 into R7 should have done A plus B into C plus D. So depending on the condition, I do this here. So in a state, there are two things that are happening. There are certain unconditional statements, whether the condition, I don't need to test any condition, this has to happen. So I do that. And then depending on the condition of the state, depending on the condition of the input here, this flag here, I do either this operation or I do this operation. And then I go back and come back here. All right. So a more general, picture of an ASM chart is, well, you may have these simple state boxes where you have unconditional statements. You simply, you're not testing any condition and you're simply doing the transfer. But more generally, this is what may happen here. You may have some unconditional register transfer statements, and there may be some conditional register transfer statements. And so now this whole, as I said, this whole thing will be modeled. So this will be converted into a data path and a controller. And controller, in this case, we are modeling it as a Mealy machine. So remember, in a Mealy machine, finite state machine, the output of the finite state machine depends not only on the state, but depends on the input also. So in this case, for example, when my Mealy FSM is in state S3, depending on this particular input, right, it will generate a set of outputs which will cause this operation to occur. Or depending on this, it will generate a set of inputs which will cause data path to cause this particular transfer to occur. Right? So, and some occur anyway. The moment you enter the state, some statements occur anyway. So some control signals are generated to cause this to happen. And then depending on this, either this to occur or this to occur. So again, my controller would be going from S0, S1, S2, S3, these states here. And now we are modeling the controller as a Mealy FSM. And depending on here, there would be different control signals which are generated for the data path. So this is a more general picture of what is really, a more general picture where we don't have simply unconditional execution of elementary register transfer operations, but you have conditional ones. So with that, it becomes more general. Now with this more general state picture here, now any complex computation, for example, we can take a, let's say a multiplication algorithm by shift and add algorithm, the usual way that you do multiplication. So now the algorithm, I can now shift and add algorithm, because it would depend on testing the bit, whether the multiplicand is 0, 1 and all the different bits, you will do different operations here. So I can take a shift and add algorithm or any other algorithm now. With this available to me, now depending on testing of some condition and doing one operation or the other, I can now execute any particular algorithm that I have in these particular ways that you see. Okay. All right. So I leave it up to you as a homework problem to take this and construct the data path and the controller and finish the design here. Yeah. This box? This box? No. So what all that I'm saying is this is one state. Everything occurs in one state.
So there are two register transfers.
No, so yeah, there is a register transfer here, which is an unconditional register transfer. And this is a conditional transfer. Depending on the condition, this will occur. So I can note that I can do several register transfers in a state. A is going here, B is going here, all this is occurring. The only thing is, to the same register, you cannot put twice, right? I can't be doing A going to R1 and B also going to R1. That I can't do. But I can do any number of register transfers. Those are independent.
But here, first you have to compute R7 and then depending on that.
No, it's not depending on R7. No, then you have to go to a different state. If you depend on the condition. Which one? Yeah, so it R6 into R7. Oh, okay, so there is I don't need to do that. See, A plus B into C plus D. It doesn't require this. There's a mistake here. This is R6 into R5. This is R6 into R5. All right. So it's a last night effect, right? So late night making this slide. So that's where the errors are. R6 into R5. Okay. So here also there is this. All right. So all that I was saying is, till now we were writing the simple state boxes with unconditional statements. Now what I'm saying is, you can have unconditional statements and you can test a condition and do conditional transfers. And that's it. That's the only general picture that I need. After that, any algorithm that you give, it can be mapped onto a picture like this here. You can break it up into elementary steps and do it in this particular manner. Yep. They're all executed in the same state. Now, what do I mean by this? As I explained, R7, R5 plus R6 goes into R7. What will happen is, the control signals to carry this operation will be generated by my controller. So all the control signals to carry that operation will be generated by the controller, and the controller will send it to the data path. And what did we say? When the next clock edge comes, the result will be lashed into R7. So when does this actual transfer occurs? At the next clock edge. So similarly, the controller will also test the condition F5. And depending on the condition, it will generate a set of control signals. Again, those are sent to the data path also. And similarly, depending on this, some control signals are sent to the data path. Yeah. All right. So maybe this will clarify a little bit further. Let's look at, these are some, new things, transfers and unconditional transfers and all that. So let's look at a very simple case here. A is transferred to R1, B is transferred to R2, R3 is R1 plus R2, two states back and forth. We agree that this can be done by a data path like this, right? R1, R2, adder goes to R3, right? Very simple data path to execute this particular one. Now, can I do this? Now, note that there is if I look at this particular one, there's fine, I can construct like this, but do you see that it's not a very efficient way of constructing? It's executing that operation, whatever operation that I want, A plus B. I want to generate A plus B. So it's executing that particular operation. But note, if I look at this particular picture here, my registers R1 and R2 are used here, let's say. But let's focus on adder. I do an addition operation here. I don't do an addition operation here. So if I have an expensive resource, let's say an adder, is used for one clock cycle and it's not used for another clock cycle. My resource utilization is like 50%. 50% of the time my adder is idle. Right? Similarly, I can think of my registers. Registers are being used for a certain part of my computation, and that same register is idle, not being used for other part of my computation. So in general, when I'm constructing this RTL design here, I should look at, am I, besides minimizing the number of states and all that, am I using my registers and adders more efficiently? So for example, can I do this? So instead of using another register R3, can I write back the result in R1? This raises all those issues of when is it written and all that. So can I do this? So A is transferred to R1, B is transferred to R2. Now R3, we are using a separate register to store the result of R1 plus R2. I'm saying, can I do this? R1 plus R2 is stored back in R1. Can I do this or not? Does it? I mean, apparently you may think, well, I'm using R1 and then it's written back into R1. Will it cause a problem? Huh? So what we are saying is this view, right? Now, R1, R2, I've eliminated a resistor R3 now. Suppose this were true, I can do that. I've eliminated R3. Now R1 results, R1 receives A, and as well as R1 receives the result of R1 plus R2. So I have to put a mux, and then this goes here. And then I have to put a select signal here. Now, can I do that? So in the first state, what happens? Let's look at, I enable all the control signals, like I will enable LD1, LD2, both will be 1 in this particular case, LD1, and I will select S0 as 0. S0 will be 0, so which means A is here. So when this happens, at the end of, so I put here 0, 1, 1. When the next clock edge comes, the results are available here in R1 and R2. Right? At the end of this, at this particular point, the results are available in R1 and R2. Okay? So results are available in R1 and R2. Now they are available, so obviously the addition has started. The addition has started, and I want the results to be stored in R1 itself. So what I do is, I place 1 and 0 here. I don't want R2 to be modified, let's say. Nothing to be stored here, so I enable it 1. And when the next clock edge comes, the result will be stored in R1. When the next clock edge comes. So note that R1, stable value of R1 is available for addition here. A stable value of R1 is available for addition, so addition is taking place here. The value of R1 will be modified when? After this clock edge. And I don't need now the previous value of R1. When I write R1 is R1 plus R2, note that when will this value R1 get modified? It will get modified here. It will get written here. By the time addition and all that has already occurred and the data is latched into R1. So I don't have a problem. I can use R1 here, R1 plus R2, I can write it in R1. Write it back. There's no issue. Okay, so that then brings us is, why am I doing it? Well, I've saved one register. I've saved one particular register, but then you may say I've added a mux. Right? But then that's why I said look at the cost here. This is a 2:1 mux. Again, all the data that I'm usually giving is for 180 nanometer CMOS technology. 2:1 mux. Its size is 5 into 5.3. And a D flip-flop size is 5 into 15.2. Right? So a mux is considerably cheaper as compared to a register here. So if you're really looking for saving in terms of area, well, I can use muxes more liberally and economize on a register here. But is there price, another price. So you've saved area, maybe by using a mux and using one less register. Have you lost somewhere else also? Note that delay, the rate at which I can run the clock is measured from one register to the next register, whatever is the delay between that. So here, so if you look at the worst case path, has only an adder plus the register delays. Here, the worst case path has register delays, adder delay plus the mux delay also. So you've added a mux delay, but if the adder delay is much larger, more complex block, then maybe adding a mux perhaps doesn't cost you that much. Okay. All right. Now, so we said that we can do this. But in this case also, if you go back, how is the adder utilization? How is the adder utilization? Still only one clock cycle it uses here, 50%. Right? Now, can I do this? Can I do this? Huh? So let's say initially R1 and R2 are initialized to whatever. Can I do this? Huh? It will give the previous value, right? So when I'm reading the present data, then what is this computing? The previous data. So it is giving me the output of the previous one. So are you seeing that what we had discussed, pipelining? Pipelining was what? We had taken an operation and broken it into two parts. One part was the present data. The other part was the previous clock cycle. So maybe I can do this also. The whole thing can be done. But note that I can't write it in R1 now. I can't write in R1 here. I have to use a separate state, R3. Because to the same register, I cannot load twice. Right? So if I write R3, R1 plus R2, maybe the whole thing can be done in one state itself. This whole operation. So while I'm reading the present data, this one is computing the previous data, previous values, and latching it onto that. So what is the, if I compare these two, what is the latency? Latency of this in terms of clock cycles? When does the data become available? 2 clock cycles? Latency? What about the latency here? Latency means from the time a data is read to the time when the output corresponding to that data appears. So how much is the latency here? How many clock cycles? 2. But what is the throughput here and throughput here? I can read a new data every clock cycle. So throughput has been doubled. I can read the data every clock cycle here. While here I was reading the data here. That's it. And then I'm waiting for this to be over and then I'm reading. Okay. So latency is 2, throughput is 1. So my point was that resource utilization, of course, is 100%. I'm using the adder in every clock cycle here. Okay. So my point is that, when I take a problem and I, intuitively we decide and we map it onto a set of states and saying how my algorithm will be executed in S0, S1, S2, S3 and all that. Just like in a finite state machine when I capture the problem as a state transition graph. We said that we may be using a lot more states than are necessary. Similarly, when I capture my problem in the form of, let's say, state-by-state description of how I'm going to execute whatever my system requires, I may be using more states than are necessary. I may be using a lot more registers than are necessary. I may not be utilizing the adders properly. So one should, if you've just captured the problem, well, functionally it is correct, but it's time to examine also, can I share some registers? For example, if I just look at this one and draw a very simple picture. Where am I using, where do I find R1? R1 I find mentioned in S0 and S1. So I just write it like this. R2 I find mentioned in S0, S2. R3 wherever here and all that. And I just go through it. And I look at now, are there possibilities of sharing? Can a register R1 which is no longer used here, no longer required here, in this and this and this? Can I now, instead of using a new register R5, maybe I can write it in R1? Why use a new register? Why use a new register like R7 and all that? Maybe I can share it with R2. So those are the things that one can write a description here. It will functionally be right, but then one has to also look at why unnecessarily use a lot more states, why unnecessarily use a lot more registers. So one can look at it and make the design. So I'll leave this particular design again as a homework problem. Look at it and see how efficient can you make, how you can share the registers and all that. Okay, let's come back to our the first problem here. So we said read A, B, C, D, y equal to A plus C and all that. Now, suppose we were, I don't know why anybody would want that, but suppose we want to design a system, an IC, which will do this for us. Okay, a dedicated IC which will add 4 numbers. All right, A plus B plus C plus D. Right, so what would our IC look like? And for that we were carrying out the design. So if I had an IC, let's say this is my IC here. I have 4 4-bit inputs, A, B, C, D here. I need to produce an output Y. And Y, as you can see here, if these are 4 bits, I may have to put 6 bits for Y. So if you add 4-bit numbers, the final result may be as large as 6 bits maybe. So I may have to reserve 6 bits here. I need to have a VDD and ground for my IC, power it up and ground here. This is a synchronous clock system, clock here. And I may add a reset pin just to get this, to reset it and then restart from the initial state here. So let's say I have this one here. How many pins do I require? 4. I have about 4 into 4, 16. 16 and 6, let's say here. 22, 23, 24, 25, 26 pins, I see. Well, let's take it. So 26 pins are there. All right, for a very simple, this thing, I need 26 pins here because I have a lot more inputs here, right? Okay, so this is how we were thinking. We were thinking that if I have to do that, and I wrote an ASM chart and say, this is how I'll do it. Okay, now when I make an IC, the IC will have all the circuitry that we talked about, but in the IC, the inputs, outputs are connected to the pins of the IC. So what happens is, in the IC, we have what are called pads. These are metal pads, and along with the metal pads, there are some protection circuitry and some buffers and all of that. Okay, so we have what we call as a pad ring, a ring of pads here. Let me show you. This will be a better picture here. Look at this Intel 286 microprocessor, 80286 microprocessor. Can you see all the pads that are there at the edges? And can you see that there are these, these wires which are bonded here? So the wire which bonds to the pad eventually goes and attaches to the pin of the IC. And that's how you have there. So in this case, as you can see here, so there is a ring of pads here. Ring of pads. And there are 68 pins that are distributed around the pad here. Right? And so this is called the pad ring. And the inside is what is called the core of the IC, the chip core. Okay, so that's the core of the IC here, and there's a pad ring here. So let's come back to our pad ring. This is our pad ring here. So 26. So I've placed an even number here, 7, 7. So 28 pins. All right, even number here. Now these pad sizes they vary from technology to technology. Let's say for the sake of discussion, I'm taking it as a 50 micron by 50 micron pad. Okay, 50 micron by 50 micron. So this length becomes 350. So my total area, if I define it as a 28 pin IC, the total area becomes 350 inside area. Inside area becomes 350 by 350 micron. 350 micron into 350 micron, which is about 10 to the power 5 micron squared. The outside area, I mean, that's the total chip area, would be 450 into 450. The outside area, right? I'm talking about the inside area. Outside area would be 450 into 450 micron. All right, at this stage, the numbers may not mean too much for you, but let's do some more calculation. So I'm taking this particular system that I've designed, and I want a dedicated IC. So this is if I have 28 pin IC, this is the area that is available to me. Okay, fine. So this is what I'm trying to implement. Now, what are the things that I have to put in that particular space? I have to put these 1, 2, 3, 4, 5, 6 registers, 4-bit registers, let's say, 6. And this is also like 4. If I use one hot coding, I may require 4 flip-flops. Or if I use binary, maybe I require 2. So anyway, one flip-flop in our 118 nanometer technology has an area of 75 micron square. So one register, which is, let's say, 4 flip-flops, for a 4-bit flip-flop, would have 300 micron square, one register here. These are rough numbers, just to get an idea, okay? 4-bit adder may be about 600 micron square. 2:1 mux that you see here, 2 inputs, 2:1 makes maybe 100 micron square. And 4:1 mux, this is 3 inputs, so I may use a 4:1 mux, more costly, 260 micron square. So if I add up total component area, maybe I require 1, 2, 3, 4, 5, and let's say another set of values here. The register area, you get multiplied by this thing, you add the adder area plus the mux area and all that. 2760, that's just the component area, wiring area, let's make it an even number, 3600 micron square, which translates into a chip area of 60 micron into 60 micron. Okay? All right, so let's, and the core area that is available is 350 micron into 350 micron. So let's put things in perspective. So the IC that we are designing, we said we are going to use 26 pins or 28 pins. So this much area is available to me. And if I look at my complexity of the circuit that I'm designing, is only 60 micron into 60 micron. Right? We added up all the areas of everything plus some wiring area estimates and all that. Rough, the area is 60 micron into 60 micron. Well, what are you doing with this? Of 60 micron into 60 micron versus 350 into 350. What fraction of the area are you utilizing? I mean, how much will it be? 6? Huh? Very small. I mean, it's like sitting in some small piece somewhere here as compared to all of this. So, so what it says is the following. Right now, what we were saying is we were thinking of designing a system, dedicated IC, and we said 4 inputs are there and all that, and we went through RTL design. But I said at this particular stage, when you're doing your RTL design, you should also look at the physical picture. How am I going to implement that? When I start looking at the physical picture, things seem ridiculous. That I have so many pins here and so much area is available. My IC is becoming so large. And in terms of this thing, the area that my chip requires is 60 micron into 60 micron. It's very, very small. So at this stage, it also would be, we were trying to economize on adder. Let me not use too many adders. Let me not use too many registers. All that is useless, right? Why am I trying to save an adder? Maybe why doing it only one adder? You can use 2, you can use 3. For this case, you can use a lot of adders are available to you. A lot of registers are available to you, right? So unnecessarily, at that particular stage thinking, well, I should minimize area. Well, your area is not decided by your chip. Your area is decided by number of pins. How many pins are there? That is deciding the area. So this is what we call as a pad or pin limited design. How many pins are there? So now at this stage, you start to wonder, what should I do? I mean, my IC is becoming too big. 350 micron here. From here to here is becoming 450. Half a millimeter by half a millimeter is becoming too big for such a simple case. What do I do? And I'm not utilizing at all the area. What should I do? Any suggestions what I should do at this stage? It's a ridiculous design, right? No, I have a lot of space. I'm not using it. So what should I do? This one. This one is, so 26 is there. Normally what we try to do is make a die as square as possible in order to get as many dies from a wafer. So we don't want to do aspect ratios which are, 3:1 and things like that. But aside from that, now you're saying that earlier we were only looking at the RTL level. Now we have brought in the physical picture also. Eventually, how will the IC be built? So we've brought the physical picture. Now you look at it. How do I reconceptualize the system? What would you like to do now? Now that you know that the pins take up so much area, won't you want to reduce the number of pins? How would you do that? Now, can I do this? Looking at this, it appears to me that why don't I use only 4-bit inputs, only one 4-bit input. And on that 4-bit input, I first give A, then B, then C. So I serially give the data. I serially give the data to my IC, first A, then B, then C, then D. And look at that, look at my chart here. If you look at my chart here, did I require all the data to be read right in the first state? Okay, I'm in the second state, I'm requiring A plus B. When do I require C? Here. Why do I need to read it here? And when do I require D? D is required here. Why do I need to read it here? Once on a particular line A has been given, then I can give on the same line, maybe B and C. So what if I think of my IC now as same VDD, ground, clock, and reset, and I have only one 4-bit input? Only one 4-bit input, and on the same input, now I reconceptualize what my IC is going to look like, and on that I give serially now. First A, then B, then C, then D. And then accordingly now you rewrite this particular one. Rewrite your this ASM chart here of how you would execute. Maybe in the first stage read A, then in the next stage read B, and then you start computing and then read C and all that. You think about how to do it here. Now if I do that, this one may be 4 here, 6 here, 6 and 4, 10, 11, 12, 13, 14. Let's put an even number, 16, a 16-pin IC. So 16-pin IC would look like this. And 16-pin IC would be, if we look at it here, 50, so 200 by 200. The core area is 200 by 200. It's a little better than before. IC area is more than halved. So more than half, and maybe utilization is a little bit better. Okay, in this case also, still 200 micron in 200 micron, I have a lot more area available because my chip area was only 60 micron in 60 micron. Okay, but still what I'm saying, so the point that I'm trying to, through this example, bring out is that at the RTL stage, when you're conceptualizing your system, well, you say, well, let me read all of them A, B, C, D here. There's a price that you have to pay for this. The price is if you're reading all of them, then you need simultaneously parallel data, large number of pins, and it has implications in terms of a large area here. And so one can read it in serially here. If one reads it serially, you are seeing that one is minimizing the area a lot. But there's a price that you may have to pay. You may end up using more number of states because you'll have to, you're not doing everything in parallel, so more number of states are required. Okay. So it's not that design, from the description which is given, the design does not, that I start from here and then I do RTL, then I do gate, and then I implement each gate and do a final chip design. So at this stage itself, one starts to think about what would my final IC look like. So one starts looking at what are the different blocks that are there and how will they fit into the area that I have. And that may have an impact on how you are conceptualizing the RTL design. The choices that you're making here, do they make sense here? So when you start looking at the physical picture, that may give feedback to you as to how you may conceptualize this and how you may implement it. Okay. All right. So we said that. Yeah.
Like suppose we have 24 pins required, then can we do like 4, 3 square to 3 pins, 3 all side, 2 squares.
If you see here, I don't think, if you look at it, the pins are not probably uniformly distributed. If you look at it, there are places where there are no pins here. 68 pins are not. So what you're saying is whether pins are 4 or 3 or 2, is that what you're saying?
So I'm saying that we can divide two groups of sides, each sides.
Normally, at least in the this thing, the pad ring is available as one single ring that you see at the periphery. That's what it is. At the periphery, this ring is available. Okay, so in that you can perhaps distribute it and all that. And I've been saying it's mostly it's a square. It's a square IC that we are talking about mostly. Okay, so coming back, so finally we said was, so as I said, we can take a problem intuitively, write down look at it and break it up into different state-by-state description of the computation. And after doing it, one should examine it and see whether all the utilization of registers and adders and all that are proper or not, and maybe try and optimize the RTL description here. I was also telling that maybe instead of intuitively doing it, there is a more formal method of carrying this out. And in that context, as I was saying, the computation that you have, what you do is you break it up into elementary computation steps. That is, every time you're doing an operation, you define a new variable. X1 is a new variable. X2, I'm adding X1 plus C is a new variable. Y is a new variable here. So whenever you are assigning, these are called, one variable is assigned only once. One variable is assigned only once that you see here. X1 is assigned here. X2 is assigned here. Y is assigned here. So like that, you break up your complex computation into these simple elementary steps here. Then we said, take those steps here. One can conceptualize them in the form of a graph. Right? One can, same thing, one can write down each operation, one labels it now, V1 and V2 and V3, and shows it here. The next step, important step now is after constructing the problem in this form, the next important step is assigning the states to each one of those operations. When will I carry this out? When will I carry this out? And when will I carry this out? So in this case, it's a straightforward V1, V2, V3. There are not too many possibilities that are there here. So we assign states to each one of them here. So that's called scheduling. Scheduling the operations into different clock cycles. Now, as I said, scheduling could be, they may be, while one is talking about scheduling, there could be time constraints, there could be resource constraints, resource in terms of how many adders, multipliers and all that. Timing may have to be minimized here. So there may be constraints on it. Now, the next step is, after I do my scheduling, okay, after I decide this is how it's going to be scheduled, the next step is how many registers are required. Deciding how many registers are required. So if you look at this particular picture here, A, register A is required, the variable A is required here, B is required here, so I've written it out. C is an input, is required here, but then it has to be available throughout, starting from here. So C is available, required till this particular point. D is required at this particular point. X1 here. X1 is here, X2 is here, and the output Y, because it's being carried in a loop, the output Y is back here, is over here. So that's how the variables are required in different states that you see. The Y is available actually in this particular one. Okay, so this is how it is required. So if we look at it, if we look at any particular clock cycle, 1, 2, 3, 4, 5, we see a maximum density is 5. Maximum density of these. So what it is implying is that maybe I can do the whole thing with a minimum of 5 registers. And those 5 registers that you see here, maybe then some sharing and all that will have to be done. So if I construct this particular picture here, from there I can say 5 registers are required. So the next thing is, I take R1, R2, R3, R4, R5. And what we have to talk about is, we have to bind the variables to the registers. So we said 5 registers are required by looking at this particular picture. So we write down those 5 registers, R1, R2, R5, and then we start binding. So we assign. Binding means we are assigning the variables to the registers. So we say A, fine, R1, B, R2, C, R3, D, R4. So straightforward till now. Now, X1, well, let's assign it to R5. And then X2. What are the possibilities for X2? What are the possibilities for x2? Any of these I could assign, right? x2 I could have assigned here. So all the possibilities, many possibilities are there, as you can see here. Y, what are the possibilities for y? All right. So what we do is, so what this step is, after identifying if you're trying to economize on registers, identify the registers here and start binding the values to those particular registers that are there. Once you have done that, once you have scheduled the operations, decided how many registers are there, and you have done the binding of the variables to the registers here, then you can straight away construct the ASM chart. All right. So what are the steps involved? Again, let's go back. If you see here, steps are: step number 1, break the computation into elementary computations, such that one variable is assigned only once, x1, x2. So every time you have to assign something else, introduce a new variable, x3 or x4. So do that. Next step, construct a data flow graph, just showing how the flow proceeds. Next, decide what state I'm going to carry out. Assign this thing here. Next, look at now the as a help towards deciding how many registers, construct a picture like this. Where are the variables used in which clock cycles? Decide a minimum number if you want.
Why do we need C right from the start?
Because see, when somebody is giving you the data may be available here, but may not be available throughout on those input lines.
Discussing that IC case,
in that we'll have to now tell, we are constructing an IC, so we'll have to tell where the data is coming from. So when one is doing a complete system design, one will tell, now you have to send the data like that. You have to send the data A and then B and then accordingly like that. So here, let's say the data is all available A, B, C, D and available for a clock cycle. So I have to latch it here, right here. Otherwise it will not be available here. Okay. So construct a picture, number of registers required, do a binding. In some sense, all these steps you are intuitively doing it. Even if you don't go through this formally, you are actually doing it. When you are looking at a computation that you have, you're deciding which state to occur, how many registers to take, which variable to put in which register. You're intuitively doing it. This is a more formal method of actually carrying this out. Okay. And once you're done with that, once you have an ASM chart here, then you can construct the data path by looking at each operation. What are the registers? What are the adders, muxes, and all that? And you can construct the controller also. Once you have that, you can construct the controller also. All right, let's stop here.